A student wants to measure the frequency of a simple pendulum. Describe a suitable method for explaining how to ensure the accurate result. Right, in a simple pendulum, you have a piece of string and a bob, and they want you to work out the frequency and also a method explaining how to ensure an accurate result. Okay, so the time period is the time it takes to complete one full cycle, so from there to there. But if you wanted to find out what the time period of that there, it's best to measure 10 time periods. Okay, so if you do 10 time periods and then time as to how long it takes to do 10 time periods, and if you do that 3 times, you can then get an average value. Make sure that, of course, after you've done the 10 times periods, you divide it by 10 to give you 1 time period. But if you repeated it 3 times, you can then do a mean to get a value of t. Well, how do you, first of all, measure the time? Well, the thing is to create something called a fiducial marker. Okay, a fiducial marker is, you could put like a pencil there, held in a clamp, or anything else that could be used for you to judge when the pendulum has swung past a point. By putting it in the middle, it's better than putting it at the ends, because the ball goes through the fiducial mark very, very quickly, so it's quite easy to judge when it's gone through it. If you put it at the end, it's sometimes difficult to work out when exactly it's reached the end, and it's going very slowly at that point there. So that using a fiducial marker, let it do 10 cycles, then divide by 10. So you time it for 10 cycles, divide it by 10 to give you 1 time period. Do that 3 times to get an average time period, and then you need to know that the frequency is 1 over the t. Okay, 1 over t. Other things to bear in mind is you need to basically get rid of anomalies. So discount anomalies would be something to bear in mind as well, to make sure you get an accurate value of the time period and therefore the frequency. So discount anomalies. Right, when a bench is fixed to, when a ruler is fixed to a bench so that the part of it extends beyond the edge of the bench, this extended part will undergo vertical oscillations when displaced and released. A student is trying to find out whether the oscillations are simple harmonic. Well, to the conditions for simple harmonic are basically that there is an acceleration. The acceleration is always towards the equilibrium point, the equilibrium. And the second thing to note is that the size of the acceleration, therefore the size of the force, is directly proportional. Keyword, directly proportional to the displacement from proportional to the distance or displacement from the equilibrium point. Displacement from the equilibrium point. They're the conditions. Okay, that's really, really key. The key things there is always say that acceleration is always towards the equilibrium. So that should be always towards. And the size of the acceleration is directly proportional to the displacement from the equilibrium point. Discuss whether the ruler will undergo simple harmonic motions when placed for the range of masses used. Right, you can see, I'm just going to get rid of some things here, so we'll get rid of the annotations. Well, consider the effect of small and initial displacements. You can see that when you put 10 grams on it, the deflection is roughly 10 millimeters. Now, at that point, then you will have whatever that is. That'll be sort of 0.1 newtons pulling down, and of course, because it's an equilibrium, there'll be a point upwards with 0.1 newtons pulling up. So the forces are equal and opposite, and therefore balanced. And you can see that as you increase the mass, okay. So the mass is increased. In other words, the force is increased. So mass will be related to the force. That the deflection increases. In other words, the force is proportional to the deflection or the displacement from the equilibrium point. So you can see that at these values here, it would undergo simple harmonic motion, because as the force increases, the distance increases, or as the distance increases, the force acting upwards increases in a directly proportional fashion. But you can see that after 30, it's no longer going up by 3, it's going up by less than 3. So at this point here, it would no longer, it would vibrate, yes it would do, but the size of the force would not be directly proportional to the distance which the ruler has been deflected by. So for this one here, you need to say, yes, it is SHM. It is SHM for small up to 30 grams, okay, and or 9 mils, but no for greater than 9 mils or 30 grams. Suggest, given reasons, how the time period of vertical oscillations would change if the ruler was moved so that the shorter length. Right, the key thing is suggest how the time period of vertical oscillations would change, and then give reasons. So the first thing that would happen is the time period will get less, and the reason is given here, that the shorter length would be stiffer, and so therefore the force restoring the ruler back to its original length will be greater, so therefore it will vibrate faster, so therefore the time period would be shorter. So if it's stiffer, it will have a higher force restoring it, the frequency will become higher, therefore the time period will become less. Okay, so F will become bigger, the restoring force would also become bigger, and the frequency would become bigger, and the time period would go down. And that is the end of that.